Okay, we're going to be shifting gears. So get out that worksheet that I handed out to every row except for Tristan's row, apparently, because I'm cool and I suck, basically. We are going to be, in this chapter, talking about where the electrons go around the outside of the atom, and also what that means in terms of behavior of our elements. So I'm going to do a quick recap. Actually, let me pull up the interwebs. There we go. So Mendeleev, and hopefully you've all watched a video at this point about him that I have talked about. But he was the first guy to really arrange a periodic table, and his periodic table was handwritten, kind of. He did it on cards, is what he did. He literally had like index cards and like arranged them in order of increasing atomic mass, and he put the things that behave in a similar fashion next to each other. So, for example, here we've got carbon and silicon. They behave like each other. We've got lithium and sodium and potassium. They all behave like each other, so they're in the same row. So this was the original periodic table. Think back to chapter 2, question mark. Why might it be a bad idea to arrange elements in order of atomic mass? Do you remember what isotopes are? Yeah. What are isotopes? Okay, so it involves neutrons that change the mass. So same element, but different mass. So like, okay, carbon. Which carbon mass do we use? Why are we using 12 and not 13? Because 13 exists. Why are we using that and not 14? 14 exists. So there was a little bit of ambiguity about how this was going to be arranged. So then this guy named Moseley, and I don't know his first name, he came along and was like, okay, but what if we did atomic number instead? Because the atomic number doesn't change. If the atomic number changes, your element changes. So I don't have to worry about which carbon I use. Carbon always has 6 protons, right? So this is how we got to our current periodic table, which looks like this, right? But also, what the heck is that chunk down at the bottom? So just for your information, and this will be helpful for you later today, it goes at the bottom because this does not fit nicely on a piece of paper. That's actually where it goes. So keep that in mind moving forward. You will also hopefully notice that from Mendeleev's periodic table to Moseley's periodic table, we also rotated it 90 degrees. So now the current periodic table, instead of things being next to each other that behave in a similar fashion, things are in the same column if they behave in a similar fashion. So we call lithium, sodium, potassium, rubidium, etc. alkali metals because they all behave in a similar way, and so we group them together. Okay, so we're going to work on periodic trends and predicting and putting things in order on Thursday, but for now, we need to look at, actually, let me go back here really quick. We're going to be looking at where the electrons get arranged in the atom. So which one of these numbers, let's look at iron, which one of those numbers tells me how many electrons I have? Does everybody agree that it's the number 26 on iron? Please, for the love of God, pick that one, okay? That is the number of electrons, and you're going to need that a whole lot today. All right, so we talked about the different shapes of the orbitals, and you watched a video, and I briefly recapped it, and it looks absolutely ridiculous, some of those orbitals, but they go in a certain order and are arranged like that for a reason. So we are going to be basically creating a seating chart for our electrons. So people who are watching this are watching me scroll through all of my pictures, which have some really entertaining things, like me dressed up in my Buc-ee's onesie. Sorry, people who are watching this video, because I am recording it. Okay. Oh no, cancel, delete that. Hate it. I have another one. Sorry, I'm trying to find the like nice clean one. Whee. Okay, apparently I don't have a nice clean one. That one it is. Yay. All right, what if I crop it? No. What if I crop it? Here we go. Okay. Crop it. Okay. Sorry, I'm having to like crop this thing because I swear I thought I had a better one. Okay. We're just gonna, it's fine. We'll use this. Okay. So, there are 3 rules that you need to know about assigning seating charts to electrons. All right. The first rule, Hund's rule. Well, let's don't do Hund's rule first. We'll do the Aufbau principle. Write this down. The Aufbau principle states that we must fill orbitals of lowest energy first. All right, electrons are lazy and don't want to be any further out from the nucleus than they have to be. So we fill the things that are closest to the nucleus first because they are lowest in energy. And then if they have to, they'll go into the one that's next higher in energy. And then the next one, and then the next one. All right, so what that means practically and what you're going to have to do is we always start at the 1s orbital and fill in order of increasing energy. And I'll show you how to use that thing in a minute so that you can do that. All right. The second rule is Hund's rule, H-U-N-D apostrophe S. This is a rule that states that we have to put 1 electron per degenerate orbital. And I will explain that in a second when I do an example, and then it'll make sense. Before pairing up our electrons. And then the last principle is the Pauli exclusion principle. P-A-U-L-I, Pauli exclusion principle. And this says that electrons cannot have the same quantum state. All right, what that means, if we think back to when we were talking about quantum numbers, and we said like we can't have two people sitting in the same seat at the same concert on the same night, right? I can't have 2 electrons that identify exactly the same. So practically speaking, what that means is if they share the same orbital, they must have the opposite spins. So those are the three rules that sort of dictate how electron configurations go, aka electron seating charts. Oh no, oh no, messed it up. Okay, it's fine. Everything's fine. There. Now I can move it. Okay. All right. So there are a couple of diagrams that are helpful for sort of understanding this. The first one, oh boy, let's see, is this one that comes from a PowerPoint. All right. You do not have to write this down, but this is to give you an idea because we follow the order here. This is the second important thing. We follow the order. We always start with 1s, follow the arrow till we get to the end of it, and then start on the butt end of the next arrow and go till we get to the end of that arrow, start on the butt end, go till we get to the pointy end, etc. So 1s, 2s, 2p, 3s, etc., etc. But if we get down to these like later arrows, you'll notice that they don't go in order because I have 4s, 3d, 4p, 5s, 4d. So I've got 4 in 3 different places that don't make sense if we're going in number order. The reason for that is we're going in order of energy. So this tells us the amount of energy, right? The reason for that, and again, you don't have to know this, but our 4s orbitals, oh no, stop that. Stop that. Stop that. Our 4s orbital is here. The next lowest energy level is 3D. So I want you to keep in mind as we do these, not necessarily are all of the same number going to be sitting together. And that's fine. Specifically, shouldn't be. Because here, 4s, the next orbital is not 4p, although it sounds like it ought to be. The next orbital in energy that's low in energy is the 3D orbital. Okay, so again, you don't have to memorize this. I'm using this to explain to you why we're not always going to go in number order. Okay, so do we remember the shapes of our orbitals? Circle. Okay, that's one of them. Which one is it? Okay, right. So S, I'm going to zoom in over here. There we go. S is a sphere. And actually, let me shrink that up. S is a sphere or a circle. And how many electrons can go in the s orbital? I was going to say, I mentioned it in my video. All right, the next orbital is p. Those guys are funny shaped. How many electrons can my p orbital hold? Do you remember? No. 6. All right, we were totally just guessing. I'm just going to tell you at this point. It was in the video, but it's more important now. All right. D orbitals are weirdos. They can hold 10 electrons. And then F orbitals are extra weird. And they can hold 14 electrons. Okay, you need to have those numbers memorized. Bless you. Write them down somewhere. Write them on your reference packet if you want. They won't be on the one that you have for your quiz or your exam, but it'll be easy access for you. You need to know s orbitals can hold at most 2 electrons. But think of it like a box. It doesn't have to have that many electrons in it. That's the maximum it can hold. Okay? So S2, P6, D10, F14. So between that information and this weird zigzaggy line thing that I put up here, we're going to be assigning seats, so to speak, for our electrons and where they go around the atom. All right, so I would also draw this on a paper. It's actually super easy to replicate. Start with one S and write all of your S's directly below it down to 7. And then directly next to it, you're going to make a column of P's, but it starts at the 2. And then you're going to do the same thing with the D's, but it starts at the 3. Right, et cetera, et cetera. And then you're going to do the same thing with F's, but it starts at the 4. So every time you do a new letter, you start one number down. Because it does. No. Because it does. You don't have to. If you drew that, that's not wrong. You're just literally never going to use them because they don't exist. So like, you can draw that if that's prettier for your brain in terms of recreating a tool, fine. It's not wrong. You're just never going to touch them. Okay. And then as far as making sure you draw the lines correctly, if you remember that you go through 2P and 3S, every other line is parallel to that. So I'm not going to give you this on the quiz. You're going to have to remember it. So figure out how to draw it. Yeah. What? I don't understand the question.
So it goes S4, D4, D4, F4. Why does it 5 and so on instead of going like that?
I don't understand the question. Okay. Maybe it'll make sense once we start doing some stuff. All right. What do you think those numbers out in front are? We've seen them before. You just may not know that you've seen them. They are our principal energy levels. So N equals 1, N equals 2 that we used for our calculations for energy transitions. Our like quantum numbers, N equals, that's what that is. Right? So principal energy level 1 only has an S orbital in it. Principal energy level 2 has S and P orbitals in it. Principal energy level 3 has S, P, and D energy level or orbitals in it. So we can get a lot of information from electron configuration. So let's do it. All right, the first thing that we have to do if we're going to do an electron configuration is we have to figure out how many electrons our element has. So how many does magnesium have? 12. So we are going to create a seating chart for those 12 electrons using this to tell us the correct order that we're in. Okay? So we always start with 1s. How many electrons can the s orbital hold? 2. So the way that we note that is we do it as like an exponent on the letter. So my 1s has two electrons in it. And what I'm going to do, and you don't have to do it this way, but you do need to do this in some fashion, is I always write how many electrons I'm starting with and cross them off as I do that. So I've used 2 of my electrons. I have 10 left because I'm going to have to find a place for all 12 of those electrons to go, right? So using this thing, I got my 1s. I get to the pointy end of the arrow, go and start at the butt end of the next arrow and just follow the arrows. So the next thing I'm going to fill up is 2s. How many electrons can an s orbital hold, Greg? Wow, Greg, you sound just like Kalasia. Weird. I love that you know, though. You just didn't listen when I said Greg. Yes, Greg, 2. All right, so now I have 8 electrons left. All right, 2s is done. Get to the pointy end, start on the butt end of the next arrow. Hopefully y'all can see. I'm trying to fit it all on the, but we filled up 2s. Now we're at 2p. We follow the arrow. So we did 1s, next arrow 2s, next thing is 2p. So how many can 2p hold, Josiah? 6. So I now have 2 electrons left. All right. From 2p, the next thing I fill up is 3s. How many electrons can 3s hold? 2. So conveniently, it fits exactly to fill up our 3s. So this is the electron configuration of magnesium. Yep. No. Mm-mm. Yep. Yeah, and if you look down here, that's what it looks like. Yep. So no commas, no nothing. If it helps you for visibility, you can leave a little bit of space, but no, they just go right next to each other. All right. The other thing we can do with this is create what's called an orbital diagram, which is just where we draw out what we just created as an electron configuration, but with orbital notation. So every 2 electrons gets a line. So my 1s looks like this. My 2s looks like this. My 2p, because there can be 6 electrons, gets 3 lines because it's a p orbital, so there are 3 degenerate orbitals. So I just used a word to answer a question for Kalasia. These lines represent degenerate orbitals. So if you remember from the picture that I said, hey, you don't have to memorize this, I'm just using it to explain, right? This shows you our 3p, for example, all have the same amount of energy. Orbitals with the same amount of energy are called degenerate orbitals. That is the name for them. And so each of these orbitals can only hold 2 electrons. If you remember when I was talking about p orbitals, I said we have one in the x orientation, one in the y orientation, one in the z orientation. Each of those 3 are degenerate orbitals, and each of them can have 2 electrons, which is why p orbital as a whole can hold 6. Does that make sense? So my d orbitals, because they can hold 10 electrons, would have 5 lines. My f orbitals would have 7 lines because they can hold 14. All right, so what we do to draw our electrons, we represent our electrons. Stop talking while I'm talking. It's really exhausting having to listen to that in the background. So our electrons, we represent with half arrows. Some people, including me sometimes when I'm feeling froggy, draw their ones like that. It's a half arrow. So like we're just missing, the other piece, right? That is an electron. So as I fill these up, remember, electrons cannot have the same quantum state, meaning if they share one of these lines, they have to have opposite spins. So in terms of an electron, it's literally a spin. So one electron is spinning this way and one electron spinning that way. However, in terms of what we write, it's an arrow pointed up or an arrow pointed down. Mm-hmm. Yeah, they're spinning and also revolving around the nucleus of the atom. So this represents their spin with the arrow. So it may not be like clockwise and counterclockwise or the way the Earth moves and backwards from the way the Earth moves. It may not be exactly that, but they spin opposite directions of each other, and this is where magnetism comes in. That's a Gen Chem 2 thing. Literally determines if something is magnetic or not. But the way that we draw it is like that. I have 2 electrons in one s. They cannot exist in the same orbital with the same spin. So I draw one up and I draw one down. Likewise for 2s, for 2p, if you remember up here, Hund's rule, 1 electron per degenerate orbital before pairing electrons up. So when I used to teach this in high school, we did something called like the Hog Hotel, and we had these rules about how pigs don't like each other and don't want to share a room. So we assign them their own room first and then pair them up if we have to. That's what we're doing with our electrons. We put 1 electron on each line, each degenerate orbital, then we can double up. So you see what I did here? You see what I did here? 1 arrow on each line. Then if we have more electrons, we can go back and double up. And then my 3s has both of its electrons in there. So there we go. You're not always going to fill up an orbital. I'm going to show you that here in just a second. But this is what it looks like. All right. Let's do the next one. How many electrons does phosphorus have? 15. So I'm going to cheat a little bit so that we can work through some of these things together. But the 15 is more than 12. So it's going to have this plus something extra, right? So 1s2, 2s2, 2p6, 3s2. So I have 3 more electrons at this point because 15 is 3 more than 12. Once I fill up my 3s orbital, I get to the end of the arrow, which means I start the next arrow. The next thing I have is 3p. How many electrons can a p orbital hold? Right. How many electrons do I have left? So I don't have to fill up the box. This box is only half full. Right. So what that would look like is just like this. And there. Just like this, except for now I also have 3p. And remember, 1 electron per degenerate orbital before we pair them up. So we're going to have some half full lines here in our final product. All right. Obviously, we need more practice, but do we have questions on this? All right. We good on how many each orbital can hold? Are we good on, hey, I need to go in the order that this thingy says because that's lowest energy to highest energy? Yeah, okay. Are we good on arrows on the lines? No, because you don't understand, or no, because you need more practice? You know what? Step 1 is acknowledging where you mess up. So I do appreciate. We're going to do more practice. I'm just kind of gauging where we're at here. All right. The next one, vanadium, 23 electrons. All right, so I'm going to start all the way back at the beginning. Give me this guy. All right, I got 23 electrons to work with, right? Where does the first electron go? What s? 1s. 1s, and that can hold 2 electrons. All right, that guy got full. So now I have 21 electrons left. Next is my 2s, and it can hold 2. So, ooh, that's not a 2. So now I have 19 left. All right. Next is 2p, and it can hold how many? So I have 13 electrons left. What comes after 2p? 3s. How many can it hold? 2. What comes after 3s? 3p. How many can it hold? 6. I've got 5 left. What comes after 3p? 4s. How many can it hold? All right, what comes after 4s? 3d. This is the first place where you see something that's out of number order. Just don't question it and be like, oh, that must be 4d. No, just write down the number it says, because 3d is lower in energy than 4p. So, 3d. How many can it hold? Right, but I don't have 10. I have 3. No, 10 is the maximum that it can hold. But we don't have to fill it up. Just like a box. Literally think of it like a box. S boxes can hold 2 electrons. But anytime I'm filling up a box, I could fill it up halfway if I wanted to. Right? Nobody says that every box has to be exactly full. Right? Okay, so now let's draw it out. All right, 1s gets its 1 line. 2s gets its 1 line. That's not a 2s. There we go. 2s gets its 1 line. 2p gets its 3 degenerate orbitals. Then 3s, 3p, 4s, and 3d. Even if your orbitals are not full, always draw all the lines, because it's actually important that we have unfilled space in the orbitals. All right, so 1s gets 2 electrons, 2s gets 2 electrons, 2p, please fill them like this. 1, 2, 3, 4, 5, 6. Parallel spins, 1 in each. Then we go back and double up. 3s, 3p, 4s, and then 3d. Looks like that. You also might see these literally drawn as boxes, but lines are the most common way to do it. She was asking me a question first. Because 3d, like all d orbitals, can hold 10 electrons. So each line can only have, you know what? Yes. 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 For every time. Yep. Okay, Josiah, what were you saying? Okay. So however many it can hold, draw half that many lines, because each line can have 2 electrons on it, right? So, yep. And again, even if you don't use them all, draw all the lines, because the fact that I have 2 unfilled d orbitals is important. It matters. Okay. Do we think we're ready to try on our own? Okay, I want you guys to do 4, 5, and 6 then. So I'm going to give you, I'm going to say 7 minutes. What? Yep. Mm-hmm. Sounds like somebody doesn't want to get out their periodic table. If you don't have this arrow thing written down already, I would get it written down before the end of class. What? If I ask for it, yes. Okay, that's actually a really good question. Blessing just asked me if you've already done the electron configuration, do you have to do the orbital diagram. If I ask for it, yes. However, I'm usually only going to ask for one. But like you're learning, so I'm having you do both here. So I'll either say draw the orbital diagram or give me the electron configuration.
Which one's the
Orbital diagram, the one with the arrows.
yeah, which one's
The electron configuration, that's the one without the arrows. So this thing that you actually finish. No, you didn't. You have an exact. Sir, is that what I wrote?
Do I have to write?
The power? Yeah. Yes, you do. Because if you don't draw the orbital diagram, that tells me how many electrons go there. I have 2 electrons in my 1s. I have 2 electrons in my 2s. That's what that tells me. So yes, you have to draw that. Wait, there's 3. What? 3 what? Oh, shoot. I think that's right. Off the top of my head. Raise your hand if you're going to have to take Gen Chem 2. Okay, for those of you who are going to have to take Gen Chem 2, orbital diagrams are important. So get the arrow business up in your head because you're going to need it. You will discuss diamagnetism and paramagnetism and look at orbitals when you're making bonds. So get that in your brains. I have not taught it here up to this point. However, I teach whatever they tell me to. So if they tell me to teach it, then yes. I have taught it before though, because I taught EPM, which is first and second year semester chemistry. All rolled up into one. Super fun. You are a skipper. And then what comes after 2B? Nothing, actually, you don't need. Yeah, height. As of right now, it's some fields, but that changes from semester to semester.
I'm not thinking of next semester, but might be next.
I have absolutely no idea what's going to be happening in the spring. Up until now, I mean, I've only been here 2 springs, and that's what we did, and I have not done a lot of things. But that's because we have so many people that get one, that somebody else is there. So it's not that I can't teach it, it's that they need it in here. Oh, no, I see it now. At the time, I was just seeing it by the corner of my eye, so I'll hold it. So this is great. Would you like to come and hug Blessing space heater? No, that's okay. She tried to melt her purse. It's kind of fun. I literally think that's what was happening. Is I think you were melting your purse with it. Because it smelled. Oh, it smelled like burning plastic. I really think you were trying to melt your purse. All right, I got like a minute and a half. Yeah, but again, it's super easy to create. Just start with 1 through 7 for your S's. And then you're going to do a column of P, but start at 2. So 2P, 3P, 4P, 5p. That's a p, I swear. 6p, 7p. And then do a column of D's, but start at the next row down. So 3D. And then do a column for F's, but start another row down. And then if you can remember that 2P and 3S have a line going through them, all of the other lines are parallel. So actually I will give you this for the quiz. It will not be on the exam or the final. Everybody hear that? I will give you the zigzaggy business on the quiz. I will not give it to you on the test. That way you've got some more time to get it memorized. Yes. Fantastic. All right. My timer is up. All right, so I'm going to put the correct answers up here. We have and so you would have, for this one, you would have everything full up until the 4P. And then you would have just 2 arrows on 4P. And then for this one, you would have everything full, including your 4P. So you should have 6 electrons in 4P for that one. And then for this guy, everything's full up until 2P. And it should look like that. All right, again, I'm shortening this because I want to introduce the next thing, and we've only got 12 minutes left in class. So I want you to go ahead and flip over to not the back of this page, but like the front of the next sheet. And I want you to take a minute to do question number 4. So not the back of that sheet, but here, question number 4, barium. Take a minute to do barium, which has 56, is that what you said? 56 electrons. All right, for people watching the video, pause it and do this. I'm about to write the answer up here. Yep. We were done yesterday by 3 o'clock. Who had lab yesterday? 2:30. It's a very short lab and very self-explanatory. Like the math, my favorite part about this lab is the math. Every single like data thing that you're supposed to calculate, it literally says this number minus this number times this number. Yeah, very few questions. Everybody was done and out of there super early. It was great. Yeah. It'd be super fun if I had the periodic table memorized, but I don't. And I'm not about to memorize it now. Hey, Josiah, are you doing question number 4 like I asked? Yeah, why?
I'm kind of like,
Uh-huh.
you know what I mean? Like, you know what I mean?
No, I don't. Why don't you explain it to me?
It's kind of like I was working so hard.
Yeah, okay. Uh-huh. So hard that you didn't even write our exponents a minute ago? Yeah. Uh-huh. Remember when I came through and was like, no, you have to write that? Remember that?
Oh, yeah, so 1S, 2S, 3S, 4S.
Yeah, except for with exponents.
Oh,
Remember that?
oh, yeah.
Remember that? All right, I'm going to give y'all, like, I don't know, however many more seconds it takes for me to get up what I need on here, up on the board. Also, have I ever showed you guys that one time that I made fried eggs and it looked like George Washington? Fried eggs, bro. Fried eggs. Okay, fried eggs, not Friday. Ugh. Okay, so here's George Washington. Yeah. The one up top had a double yolk and it looked like George Washington by the time I got done with it. Anyway. No, it totally, really?
It just looks like 2 eggs.
Really? You're telling me that that does not look like that? You're really telling me?
Oh, you talking about his eyes?
I'm talking about the whole, it looks like a bust of George Washington. Thank you. Thank you. I'm not a crazy person. You guys are just being mean. All right, here's the answer. All right, so this was really long and exhausting. If I asked you to do the next one, it's even worse because Neptunium has 93 electrons. But I'm going to show you, and no, you don't get to choose this. I will tell you which version to do. I'm going to show you the short way.
Okay.
All right, it is called the abbreviated or the shorthand or the noble gas configuration. There are several ways that we can call it. And we will get more practice on this on Thursday, the first part of class. I just wanted to introduce it to you today, but because we don't have time. But so I'm doing radium number 9, which has 88 electrons, which is here. All right, step number 1. We go up 1 row and all the way to the right. And we get that noble gas and put it in square brackets. So for radium, I go up 1 row and all the way over. Radon, I'm going to put that in square brackets. When I do that, that represents however many electrons radon has. In this case, 86 of my 88 electrons. So this is going to be like really small. Okay. Then to figure out what to write next, we go back to our element. Again, we're over here at radium. And then whatever row that's on, we start at that S. All right, so radium is on row 1, 2, 3, 4, 5, 6, 7. So I'm going to jump in at 7S. It is always an S orbital that comes after a noble gas, always. And you figure out what S based on whatever row your original element was in. So radium is in the 7th row. I'm going to start with 7S and just continue. We're just jumping in and continuing from there. So 7S can hold how many electrons? All right, this was 86. That is all 88 of my electrons. Instead of that like full paragraph of a thing that it could have been if I did it the long way. So we have ways to shorten it. All right. By writing radon in the square brackets, that includes all of the electrons in all of those orbitals. All right.
We can't do this all the time.
You can do it when I tell you to do it. Yeah. I mean, straight up, I'm going to ask you to do it both ways on the quiz. So, yes. You have to know both ways. So you would rather have done this plus a whole bunch instead of just this? No. All right. So again, we will come in and actually do some practice on this first thing on Thursday. And then we will have a nice long discussion about periodic trends. Listen up. There are videos to watch. There's like a lot of them. Like 6 or 7. But they're shorter. They're like, no. They're like, one of them's 4 minutes, one of them's 5 minutes. There's one that's like 8 minutes. So they're shorter because I've broken them down into talking about each trend individually instead of talking about all of the trends on one video. So watch those. You can break it up into short little bits. Just get those watched, okay? Okay. Bye, y'all. See you later. Can I please?
Do my lab grades, please.
Yes.
Thank you.
I've been trying to get caught up on things.
Oh, I apologize.
No, you're good. I'm working on it. I just